So this is a problem that would be harder to solve with the kinetics and the equations of motion. So kinetics and kinematics would be trickier. But when we use energy concepts to solve a problem like this, it gets pretty easy. So a 40-kilogram boy sliding down a smooth slide. So essentially we're assuming there's no friction. He starts at rest at A, and we want to know his speed when he gets to B. And then it's also bringing in a bit of kinematics here. No, kinetics. It's talking about radius of curvature. So what's the normal force? So we're talking here about centrifugal and centripetal forces. It's looking for the reaction the slide exerts on the boy when he's at B. So that reaction is going to have to balance gravity, and it's also going to have to balance the centripetal force, where it's going to provide the centripetal force at that point. It's going to balance the centrifugal force as that slide changes its direction. So the key to this problem is to notice that if you drew a free body diagram of this boy, so the only forces acting upon him, there's no friction, so the only forces acting upon him are the gravity, which is his weight times 9.81, so 40 times 9.81. So it's the gravity and the normal force. But the normal force, because at any particular point his direction of travel is perpendicular to the normal force, that normal force is going to be doing no work whatsoever. So the only thing doing work is the vertical force. And so the work done is going to be that force times the distance traveled in that direction. And so it's the total work done will be the gravity times the total vertical distance. So that's going to be the work that's done. And that's going to be turned into kinetic energy at the bottom. So using this equation. So let's have a think about that, or let's just start with the equation, I think. And so, we are going to be using the net work done is equal to the change in kinetic energy. So V, and I think they're calling that point B, so we'll call that VB squared minus the velocity at A squared. Now, I seem to be zoomed out a bit here, that's better. So the only force that's doing any work is the gravity. There is no other forces doing work, as we just talked about. So therefore, we're going to have mg times y b, so let's change it yb minus ya is going to be equal to a half times, we could have put some more numbers in there, we'll write this out first. So vb squared minus va squared. So let's stick some numbers in now. So we're going to have 40 times 9.81, and that force is in the negative direction. So it's really negative if we're taking y positive like so. So it's going to be the negative 40 times 9.81 times. So yb depends where we take the 0, but let's take yb as being the 0. Well, it's telling us where to take the 0, that's the x, so yb, take it as 0, minus 7.5 is where he started from, is equal to, I've lost my m, half times 40 times, now VB is what we're trying to find, and VA was 0, and so we can do, well, we'll just write it in for now, 0 squared. Now, we can cancel some stuff here, so it wouldn't really matter what speed this boy was going at, because the mass would cancel out, and so we're going to get this minus, doesn't cancel out, it's not minus 40 on this side, so minus 9.81 times minus 0.75, so that's just going to be 9.81 times 7.5. 9.81 times 7.5 is equal to 73.58, say, 73.58 is going to be equal to a half the velocity at b squared. So velocity at b squared is just going to be 2 times that, which is 147.15. So VB must be equal to the square root of that, which is 12.13 meters per second, which is pretty fast. Cool. I think that's answered the first question, hasn't it? Yeah, and so all of the work done by the gravity is going to turn into kinetic energy because you're not losing any energy to friction or anything like that under the assumptions we're making. In reality, you would lose a little bit. There's going to be a little bit of friction there. And so velocity at B is 12.13 meters per second. The part B is asking us for what's the normal reaction from the slide onto the buoy at B. So let's just draw a little free body diagram of that. I haven't really got an A and a B. I'm just thinking questions part A, question part B. So he's down at the bottom there, sliding along, and the slide is curved, and rho, let's tidy that up. Show what rho is. Assuming the curve's not changing too much. Just show it's really just indicating. I'm just saying if the curvature was changing, then it might be different by the time the point I'm pointing at, but that doesn't matter. We're just going to ignore that. So 0.667 meters. We were trying to draw a free body diagram. We were, so I can't really draw the slide if it's a free body diagram. So let me just draw this wee fella again. So what forces have we got acting on him? We've got weight, and then we've got the other thing we've got acting on him. It's a bit hard to show them because it's in the same direction as the weight, which should be drawn vertically downwards. But we have also got the centrifugal force. FCF. I guess I should draw that dashed because it's not the right point of application. And then we're going to have a reaction to that. Now both of those should really be vertical, but I don't want to waste your time redrawing them. We're going to have a reaction like so. So that reaction, so let's call it RB actually, because it's at point B. Time's going to do that. RB, let's call it RB, is equal to, so it's going to be mg plus the centrifugal force. So it's balancing those two forces. So FCF, which is going to be 40 times 9.81 plus, so FCF is mv squared over rho. Got to learn that, got to learn it. You're not going to be given that equation in an exam. And similarly for the energy, got to learn half mv squared. So that is going to be 40 times 9.81 plus 40. We just calculated the velocity, 12.13 squared divided by rho was 6.67 was the radius of curvature of the slide at that point. So therefore we're going to have 40 times 9.81 plus 40 times 12.13 squared divided by 6.67, which is equal to 1275 newtons. Just quite a lot, so that's like 127 kilos. So you imagine this kid's only, if we're just doing approximately 127 kilos would be the equivalent weight. So that's the kind of equivalent, what am I trying to say here? Yes, it's the equivalent weight that boy would feel. And he only weighs 40 kilos, so he's getting a fair old push at the bottom of that slide there because he's getting turned, his direction is turning. So you're getting that centrifugal force. So like 3G or something, is it? Something like that. So that's that one. And so in this case, it would be hard to see how to solve that with kinematics. So the kinematics and kinetics tends to work better when you've got problems going in a straight line, where you've got some kind of curved path or something like that. It tends to be easier to use the energy equations. So I think I've got one more example to work through, and then we will be done. And you can try the tutorial.